Okay, number one. So this week we finished talking about the definition of the derivative at the end of the lecture 4.2, and we got into our algebraic derivative rules. So first, number one deals with the definition of the derivative. Number two, we cover in great detail the algebraic derivative rule. So let's start with number one. It says, here's a function 1 over x. Use the definition of the derivative to show that f prime x is negative 1 over x squared. So here we need the definition of the derivative, which remember is limit as h approaches 0, f of x plus h minus f of x all over h. So we're working with this function. We're going to conclude that the derivative is negative 1 over x squared. Well, we want to conclude that. So what's f of x plus h? Well, replace all x's with x plus h. So 1 over x plus h minus f of x all over h, and this is still the limit as h approaches 0. So right here, if you try a direct substitution, you will get a 0 over 0. But we have, yes. Is there a question?
Mr. Cameron.
Yes.
So when we make like the zoom ins, you should like disable the mic by default. Sometimes I'll be joining the class and then my mic is still on by mistake when I first joined. That's all.
Okay, that's okay. If there's extra noise, I can always go and mute things. But I didn't hear any extra noise, so that's okay. So here we have this 3-tiered fraction. So first, I'm going to deal with the numerator of this fraction. So I'll deal with this 1 over x plus h minus 1 over x. The common denominator in that numerator would be x plus h times x. So I'm going to write that. I'm going to put the x first. So there's our common denominator in the numerator. So over here on x plus h, we need an x here. So we also need an x up there. 1 times x is x. Here we have a negative. And over here we need an x plus h in that denominator. So we also need an x plus h in that numerator. And there's a negative on all of that. Any questions about that?
Professor, what did you do before? You times the what did you do before?
So up here, we combined these two pieces in the numerator. So the common denominator in the numerator is x times x plus h. So that's what we have here. And then to get the common denominator on this piece, we need to multiply by x. 1 times x gives us this x. To get the common denominator on this piece, we need another x plus h. So we have 1 times x plus h with a negative, which gives us this negative 1 times x plus h, times all of x plus h. So the common denominator here is that product. Now next, I'm going to do 2 steps of simplification. First, notice that this overall numerator, the numerator of the numerator, distribute the negative 1, you get x minus h. X minus x is 0, so you're left with a negative h up there. So this piece of the numerator is just negative h. And now we still have this x times x plus h. I'm going to write this like this, negative h over x times x plus h. So right here, the numerator simplifies to that, but we're dividing this all by h. So remember, when you divide by h, you can reduce this overall fraction by multiplying by the reciprocal of h, 1 over h. And instead of dividing by h, we'll treat it as multiplying by 1 over h. And doing that, notice, puts another h in that denominator. So we simplify the numerator, and then that's terrible h. That's a better h. And then we multiply by the reciprocal of h. We still have not taken a limit yet. But right here, notice if you do a substitution, h equals 0, you again get a 0 over 0. But fortunately, all the terms, well, both of the terms, have an h on them, so we can cancel out an h from each piece. And what are we left with if we do that? Up here, we're left with a -1. Down here, you get rid of the h, you're left with an x and an x plus h. So we did all of this algebra, and now we can take the limit by substituting h equals 0, because when you do that, you get -1 on top. X times x plus 0, which is x, and x times x is also known as x squared. So here we did show that the derivative is what part A tells us it is. Let me put the camera down a little. Any questions about, did that work? Yes. Any questions about this one?
The for the bottom of the part where it's -1 and x times x plus h. How did you get rid of the h again?
Well, here there's an h on each piece, so you can divide everything by h, or you can just, h divided by h reduces to 1. So we just canceled an h from each thing. Cancel an h from up there, you're left with a -1. Cancel this h, you're left with x and x plus h. Any other questions about this one? Where did I put my eraser? So part B of this asks, find an equation for the line tangent to 1 over x. So tangent line when x equals 5. So we need a tangent line when x equals 5. Well, we need a line. When we need a line, we need a point, and we need a slope. Well, this function is 1 over x. So the point, well, the x value is 5. The y value is given by the function at 5. 1 over 5. Now the slope, well, remember the derivative is defined to give us slopes of tangent lines at given points. So here, the derivative evaluated at 5 will give us the slope we want. The derivative is what? -1 over x squared, so -1 over 5 squared, -1 25th. And now, well, we didn't just want the point and the slope, we wanted an equation for the tangent line. So we get y minus the y value equals slope times x minus the x value. Any questions about part B? And you don't have to simplify that. That's, you have better things to do with your time than simplify that. So any questions about part B?
What worksheet is this?
This is worksheet 5. Any questions about part B? At part C, at which x value does this function have a horizontal tangent? Well, what does a horizontal tangent look like? Well, if there's a function, that's not this one. A horizontal tangent is a tangent line that's horizontal. So in particular, it's a tangent line. That's a great job. Where the slope is 0. So we need to find all tangent lines where the slope is 0. Well, the derivative's not written, but what that reduces to is finding all x values where f prime x equals 0. Well, what's f prime? That was given in A and found in A. Guess I'm going to go up here for it. So C set f prime equal to 0. So we have -1 over x squared equals 0. Where does this equal 0? Well, let's get rid of the fraction. Multiply by x squared, or negative x squared if you so prefer. Multiply both sides by x squared, you get -1 equals 0. Well, -1 equals -1. -1 does not equal 0. So this means that's never true. So this means there are no x values which satisfy this. So we'll just say, maybe I could say there are at the beginning and make an actual sentence. There are no such x values which make the derivative equal to 0. Any questions about that? So right here, we showed this algebraically. We could also have shown it geometrically, because we know what the function 1 over x looks like, what the graph of the function 1 over x looks like. I guess I'll erase that. So I don't want the function too low because I won't be able to do what I want to do. So right here, we have 1 over x. And we're looking for, in part C, if you don't want the algebraic approach, I guess it's more of a calculus and algebraic approach. If you want where the tangent line is horizontal, well, you can look at tangent lines. So here I have a stick, and we can use this to model tangent lines. It's not a perfectly straight stick, but you can use your imagination that this is a perfectly horizontal stick. So here we look at tangent lines. Are any of these horizontal? Well, no, none of them are horizontal. None of them are horizontal. You will notice as you keep going toward infinity, the tangent lines do approach a horizontal tangent, but they never get there. There's always this slight downward slant on the tangent lines as x gets larger. And similarly over here, you'll never have a horizontal tangent line. But of course, as you keep going, in this case, toward negative infinity, you do approach a horizontal tangent line. So you could have observed that geometrically as well. I keep a stick around for using tangent lines, and back when I held class in person. You walk into class with a stick. That's any questions about part C? This stick, by the way, is from Beltsville State Park, which is like a half-hour north of here in Carbon County, Pennsylvania. Here being Allentown and Allentown. So any questions about number 1? Okay. Now number 2, we're going to find f prime x, find the derivative, and here we're not told to use the definition, so we can use the algebraic derivative rules. so we will use them. So there were 6 algebraic derivative rules. We'll talk about them as they arise. The first one says if you have the derivative of something plus something else, or minus something else, you can do the derivative one at a time. So in particular for this one, we have 3 things added together here. We can do these derivatives one at a time. So we can work on x cubed, then we can work on negative 4x, then we can work on negative 5. So that's a convenience, actually a convenience of limits that applies to derivatives as well. So we can deal with these one piece at a time. How do we deal with x cubed? Well, we want the derivative of x cubed. The second rule, this plus minus rule, was the, I forget if it was third or fourth, probably third. For x cubed, well, the second rule in our list told us how we could take derivatives of x to any number. The derivative of x to any number, bring the number out front, multiply, subtract 1 from that number. So here for x cubed, we have n equals 3. If n equals 3, what do we have? Well, we have 3x to the 3 minus 1. That's a 3 up there. 3x to the 3 minus 1. Any questions about dealing with the x cubed? Of course, that simplifies to 3x squared, but we'll get there in a moment. Okay, next, we have negative 4x. Well, another derivative rule, which is, I believe, rule 3. It might be rule 4. Oh, no, which I believe is rule 4. It might be rule 3. It should be rule 4 because, yeah, maybe, I don't know. I haven't looked at that list in my belief. But it's the rule, the constant times a function rule. So if you have a constant times a function, you want the derivative, well, you can pull the constant down and just take the derivative of the function. So here, if you have a constant times a bunch of things with x's, well, you bring the constant down and take the derivative of that thing with all those x's. So in particular, for negative 4x, we can pull the negative 4 down and just deal with the derivative of x. Well, how do we take the derivative of x? Well, x is x to the first. We would apply the power rule. We would get 1x to the 1 minus 1, which is 1. Well, it's right number 1, which is 1 times x to the 0, which is 1. So here, we would have negative 4 times 1. And in that, we used the constant times a function rule, and then the power rule with n equal to 1. And finally, the negative 5, well, negative 5 is a constant. The first rule in our list says the derivative of a constant is 0. Negative 0 is the same as positive 0. And then just simplifying this, not simplifying, but combining the numbers that can be combined, you get 3x squared minus 4. And do notice with this middle term, constant times x by the power rule and the constant times the function rule, the derivative is just, in this case, negative 4. It is just the constant times 1.
Can't you just use the power rule for that second part of the equation too? Because you would have just 4 times 1 and then 1 minus 1 is 0. So 1,
Yeah,
like, would that work in every situation?
It would for x to the 1, yeah. But you know, this the x to the 1 minus 1 does simplify to 1, and all that equals 1. So if you do that, you shouldn't leave your answer like that. Should rewrite that as 1. But yeah, you could do that. Any other questions about this first one? Things like this middle term, we're going to be doing derivatives for the next like 7, 8 maybe 9 weeks. And even after that, they'll sort of show up. So going from -4x to -4, we're gonna, it's not an exaggeration to say that that will probably show up 50 times in this semester. So, you get used to doing it without the power rule. Any other questions about A? Plus x to the -3 plus 10. Okay. So part B, we have several more power rules and the constant times function rules. So here, 5x cubed, well, we know how to deal with x cubed. Derivative of x cubed using power rule became 3x squared. So we have a 3x squared from that, but then there's this 5 in front of it. We can just carry the 5 down, multiply by 3x squared. 5 times 3 gives us 15. Similarly, for this next one, well, ignore the -4 for now, and we have an x squared. How do we do the derivative of just x squared? Well, again, we would use the power rule with n equal to 2. If n equals 2, what do we get? 2x to the 2 minus 1. 2x to the 1, which is just 2x. So we have a -4 times a 2x. -4 and 2 make a -8. Any questions about the first two pieces of this one? Okay, next we have x to the -3. Yes.
For the eights, for the -8x, how did it go? How did the 4 go to an 8? I know how the power rule for it.
Well, here we have x squared. The derivative of x squared with the power rule is 2x. So the x squared gave us a 2x, and then -4 times 2 gave us -8. Any other questions about the, yes?
Wait, never mind.
Any other questions about these first two pieces? Okay, next we have x to the -3. Well, again, that's x to a number, so we can use the power rule. That tells us what? X to the n has derivative n. X to the n minus 1. So we have a -4 there. Because we have -3x to the -3 minus 1. -3 minus 1 is -4. So it's very common to make the mistake of writing a -2 there, because as you can see over here, positive numbers show up a lot more than negative numbers in general. And when you do these, you become very used to going from 3 to 2. So when you're dealing with a -3, it can be kind of instinctive to want to go to a -2. So whenever I have a negative exponent, I like to slow myself down and be sure I'm subtracting 1 from the exponent. So -3 minus 1 is -4. 10 is a constant. So again, derivative of 10 is 0. Any questions about part B?
So for 5x3,
Yes.
how do you go from 5x3 to 15x2? I didn't get that part yet.
So here, it's just like the second one where we had -4 times 2x, but here we're going to have a 5 times the power rule applied to x cubed gives us 3x squared, and then 5 times 3 gives us that.
How's the x equal x? How did the x to the power of 3 equal 3 x to the power of 2. I don't understand where the 3 has come from. Yes.
Well, we're using there's the algebraic rule for taking derivatives says that the derivative of x to the n is always given by nx to the n minus 1. So here we want the derivative. We want this new function. And to find this new function, we have to follow, well, we can follow this rule to find the new function and the other rules we discussed. But here, going from x cubed, if n equals 3, you get 3x to the 3 minus 1. So 3x to the 2. And then 5 times 3 gives us the 15. Any other questions about part B? Okay, part C. Let's see, what do we have? 7x to the 11, x to the 8, negative 3x to the 6, positive 4x to the 4, positive 3x to the 2, negative x, plus x to the negative 1, minus 5x, negative 4, plus 9x, negative 9, minus 9 plus pi. So for this problem, it combines everything we discussed in problems in parts A and B, and with a lot of writing. So here we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 power rules it looks like. So I'm just going to write this answer, and then you can compare this to the answer that you got. So f prime x, 77 x to the 10. So here, I probably should have made sure I wrote the whole problem correctly. So here we have many power rules. So in the first one, we have 7 times 11x to the 10th, which gives us 77. And then the next 4 pieces are similar. 8x to the 7th, negative 3 times 6 gives us 18. Decrease the exponent. Someone should have yelled at me. I wrote 16x to the 4. It's always good to go through and check your work like I was just doing, because you can see if you forgot to do something like subtract 1 from the exponent. So here, 4 times 4x cubed gives us that 16 and x cubed. For the next one, 3 times 2x. Here we have negative x. So remember, negative x is just negative 1 times x. Derivative would be negative 1. And for these next 3, we have some negative exponents. So here, negative 1 comes down, subtract 1 gives us negative x to the negative 2. Now you could also use the remark I did. And for this, you don't have to get rid of negative exponents. As we do applications of these, we will find writing them as fractions is convenient, but that's not for a couple weeks. Well, maybe it's, about 2 weeks. Here, negative 5 times negative 4 gives us this positive 20. Subtract 1 from the exponent. Here, positive 9 times negative 9 gives us negative 81. Subtract 1 from the exponent. Pi is a constant, so the derivative of pi is 0. Any questions about part C? part D, we have this. Now, the power rule can be applied to non-whole numbered exponents. So in particular, So in particular, we can apply power rule to this first thing and get what, 9/2 x to the 7/2. But how can we deal with this and this? Well, we could use a quotient rule. I would strongly recommend against that because it's a lot more work than is necessary for these middle two. Another thing we can do is write these as x to some power. So root x, remember, is x to the half. So if that's in the denominator, we can write that as x to the negative half in the numerator. And similarly over here, we have x to the 1 in the denominator, so that becomes x to the negative 1 in the numerator. And then e is e. And now, once we write them as x, once we write all of these as x to some number, we can take the derivative using a bunch of power rules. So what do we get? Well, x to the 9/2, remember it's n x n minus 1. So x to the 9/2, n equals 9/2, we get 9/2 x to what? Well, we need 9/2 minus 1. 9/2 minus 2/2, 7/2. Should probably write that a little lower. So again, a power rule, bring the 9/2 down, subtract 1 from the exponent. Next, well, let's deal with that -4 in a moment. What do we get here? We get -1/2 x to the -1/2 minus 1. Well, -1/2 times -4 becomes a +2. Half of 4 is 2. Negatives cancel. And what's our exponent on x? Well, -1/2 minus 1. What do we have? -1/2 minus 1. So what is that? -1/2 minus 2/2, -1 minus 2, gives us -3. So we get 2x to the -3/2. And similarly here, well, we actually did this one in the previous question. -1 goes down. -1 minus 1 is -2. So we have a few power rules. E is a constant, derivative is 0. So we have a few power rules. -4 times -1/2 gave us that +2. Any questions about this one? Okay. What's next? This was D, so we probably have E next. So part E is really drilling fractional exponents into, or drilling using power rule with fractional exponents into your minds. So what do we have? X to the 17/7 plus 5x to the 6/5 minus 4x to the half plus x to the -4/5 minus 6x to the -8/3 plus log 7. Then you step back and make sure you wrote everything correctly. x to the 17/7, 5x 6/5, negative 4x to the half, x to the negative 4/5, negative 6x, negative 8/3 log 7. Okay. Well, here, again, we have a bunch of power rules. And throwing extra fractions in them makes it a little more inconvenient. But we can still use the power rule on each piece, including the constant. So what do we get here? Well, we have x to the 17/7, 17/7 x. Now this is probably going to extend across two lines. And what's our exponent? Well, we need 17/7 minus 1. 1 is 7/7. 17 minus 7 is 10. Well, then we keep going. We have x to the 6/5 multiplied by 6/5. 6/5 times 5 equals 6. And next we need six fifths minus 1. Well, 1 is 5/5. 1 is 5/5. 6 minus 5 is 1. So we have plus 6x to the 1/5. Any questions about those first two parts of this? Okay, next, bring the 1/2 down. Negative 4 times a half, negative 2. X to the half minus 1. Half minus 1 is a half minus 2 halves. So that's negative 1/2. Well, we can also put negative exponents in this, as we do here. So next we have x to the negative 4/5. Bring the negative 4/5 down. X to the negative 4/5 minus 1. I guess I'll write that here. Negative 4/5 minus 1. Well, 1 is 5/5. So we have negative 4 minus 5. Negative 4 minus 5 is negative 9. And the last piece we have, I'm going to write the answer here. And then I'll talk about it, then write it. No, I will, yes, talk about it, then write the answer. So we have negative 6x, negative 8/3. Well, how do we do this derivative? Negative 6, and then we have a power rule on x to the negative 8/3. So we have negative 8/3, x to the negative 8/3 minus 1. Negative 8/3 minus 1, negative 8/3 minus 3/3. Negative 8 minus 3 is negative 11. So on that, negative 6x to the negative 8/3, negative 6 carries through. Power rule on x to the 8/3, x to the negative 8/3 gives us negative 8/3 x, negative 11/3. But these numbers here simplify a little, and the negatives cancel. 6 and 3 make a 2. 2 and 8 make a 16. So we have 16x to the negative 11/3. Log 7 is a constant, derivative is 0. Natural log. Just checking to make sure I didn't make a mistake. Okay. Any questions about part E? Now the power rule shows up every week in calculus from now on, so there is reason to go over many examples of it, especially with all kinds of exponents. Part F. Okay, I'm going to write it down here. So thus far, we've covered 4 of the 6 derivative rules, algebraic derivative rules. Part F covers the 5th of the 6th, potentially. F of x equals x cubed minus x squared plus x plus 11 times 5x to the 4 minus 2x minus 1. So here, we need the derivative. You could, if you want, multiply all of this out. You get 12 terms. Some would combine. You'd have a bunch of power rules to apply. Or you could, and that would take, that would take a few minutes to do that. Another thing you could do is observe that this is written as the product of 2 things. And we have a rule that tells us how to take the derivative of a product of 2 things. Now, what does that rule say? Well, does it say this? F prime of x equals, so does it say this, I'll throw a question mark there to mean, does this equal, well, what's the derivative of this first piece? 3x squared, negative 2x to the 1, so negative 2x, positive 1, derivative of 11, 0, 11 is a constant, 5x to the 4, 20x cubed, negative 2x, gives us negative 2, negative 1 gives us the derivative of that is 0. So what I did here was I went through this, and when we were doing limits, we were able to do that. We were able to find a limit of a product by looking at each piece, provided the limit existed. But here, are we also allowed to do the derivative of the first, which is, this is correct, this is the derivative of the first, this is the derivative of the second. Are we allowed to do that? Well, we aren't. We cannot do the derivative like that. So maybe I'll scribble through it in blue. Oh, that's not really working well. Now it's working okay. We cannot do the derivative like that. To do derivatives, we have derivative rules. And the rule for a product does not say that you can do it one piece at a time like we did for sums and differences. The rule for derivative of a product says the derivative of a product is the derivative of the first times the second plus the first times the derivative of the second. So if you have 2 things multiplied by each other and you want their derivative, you would need to follow this rule, unless you want to distribute all that, but I'm not going to. So how would that be applied here? Well, we just follow these 4 pieces, 5 pieces if you include the addition sign as a piece. So how do we take this? Well, maybe I should move over a little more. Well, what does this say? Derivative of a product, we have 2 pieces. Derivative of the first. Well, we already did that in the incorrect answer. So there's the derivative of the first. A few power rules, some constant rules. So we have derivative of the first, then we need the second. So we have so far derivative of the first times the second, but now we need this other piece. So plus first those signs right. Yeah. Plus the first times derivative of the second. Derivative of the second, 5 times 4x to the third, so 20x to the third, negative 2. And this is correct, and of course you don't have to simplify. Any questions about this one? So to take the derivative of a product, you need to use the product rule. Part G.
Sorry, I actually have a question about the last part of that one. So wouldn't
Yes.
it be 20x cubed minus 1?
It wouldn't be. It would. So here, derivative of negative 2x, constant times x. The negative 2 carries down. Power rule on x would give you, what, 1x to the 0? So you get negative 2 times 1x to the 0, which is negative 2. And
Okay.
here, negative 1 is a constant, so the derivative is 0.
Okay, I see now. Thank you.
Any other questions about, wait, did I write that wrong? No. Any other questions about part F? Okay, part G, same function, except we're writing it as a quotient instead of a product. And just like products, we can't do the derivative of a quotient one piece at a time. Derivative of a quotient has its own rule when the denominator is defined. Derivative of a quotient is given by the bottom. Derivative of a quotient is given by the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So in the product rule, we had 4 things and a positive sign to keep track of. For the quotient, we have 5 things and a negative sign to keep track of. So we need bottom, derivative top, minus top, derivative bottom over bottom squared. Well, okay. Bottom. Great. 1/5 of the way there. Derivative of the top. Well, some power rules. 3x squared minus 2x plus 1 plus 0. Okay. Minus top. X cubed minus x squared plus x plus 11. Subtract all of the top, not just part of it. And also multiply all of the top by derivative of the bottom. 20x cubed minus 2. And it would be unfortunate if we stopped there because we went through all that work and did not get full credit because we also need to write the bottom square in the bottom. All over bottom square. All of the bottom square. Don't have to simplify. There will be times where we will use the derivative for certain things, and in those cases, it'll be convenient to simplify it a little. But for just doing derivatives, you don't have to simplify. You shouldn't simplify. Actually, you will be told on tests directly, do not simplify. So here we have bottom, derivative top, minus top, derivative bottom, all over bottom squared. And if you do in the future have to simplify, they will be convenient. They won't be. So any questions about part G? Okay, any questions about number 2? So we have those 6 derivative rules. After exam 1, we're going to learn 16 more derivative rules. Okay. Problem 3, let f of x be this function. Find an equation for the line tangent to this function when x equals 1. So we need tangent line when x equals 1. Okay, we need an equation for a line. So we need a point. We need a slope. Well, what's the point? The point is x equals 1. What is the y value when x equals 1? This is a 7, not a 2. What is the y value when x equals 1? Well, f of 1, maybe I'll write it lower. F of 1 is what? 2 times 1 is 2 plus 1 is 3. 4 times 1 is 4. 4 minus 7 is negative 3. 3 and negative 3 make negative 9. Okay, so we need a point, we need a slope. Well, remember, the derivative is set up to give us the slope we want. So we need to evaluate this derivative at 1. I don't see a derivative anywhere. So we have to find this derivative. Now, for this one, I will show 2 different ways you can find this derivative. Now, in problem 1, part F, you could have distributed everything out and gone from there, but that would have given you 12 terms, and it would not have taken less time than using the product rule. Here, the 2 ways take approximately the same amount of time, so I will show 2 ways. So one way to find f prime of x. One way to find it, well, we're going to use the product rule here. So f prime of x, using product rule, we have these 2 pieces. Derivative of the first is 2, leave the second alone, plus the first. Derivative of the second, 4 times 2x, gives 8x. Derivative of negative 7 is 0. Well, there's f prime. And we need to evaluate that at 1. So what do we get? So we have 2 times negative 3, 4 minus 7, plus what? 3 times 8 times 1. So we have 24 minus 6, which gives us 18. So notice in substituting x equals 1, I didn't use any simplified form. I just threw x equals 1 up there. You could have simplified that and then substituted it. I didn't want to do that. Well, let's finish this question now, and then I'll show the other way to do that. We have our point and our slope. So an equation, y minus negative 9, y plus 9, equals slope 18, x minus the x value. So any questions about, well, the first way to find f prime here? Or anything else in this question that's written? Okay, the other way we could find f prime is if we distribute all this out. Well, what do we get? I'll just write it here. 2x and 4x cubed give us an 8, along with 3 x's. 1 and 4x squared gives us a 4x squared. 2x and a negative 7 give a negative 14x. 1 and negative 7 make a negative 7. So this function, another way of writing this function is here, and then you can find, so I'll say another way to find f prime. So you could have distributed all this out and then found f prime using the power rule on all this, you'd get what, 24 x squared, you'd get 8x, you'd get negative 14, you'd get 0, and then let x equal 1, you'd also get 18. 24 negative 14 make 10, 10 and 8 make 18. So any questions about, you don't have to do both ways, of course, if you want to multiply it out and then use power rules, that's fine. If you want to do the product rule, that's fine. And I think they probably took about the same amount of time. So whichever you would prefer to use here. But are there any questions about number 3? Okay. Any questions about anything on this worksheet? Okay, I'm going to talk about a couple of the homework problems. Solutions are currently posted. And I will also send an email with some information on homework problems once I send all the feedback. Let's see. Number 2. Negative 2 over root 5 is the correct answer. Many submitted positive 2 over root 5. It is negative. Some of you, there were a few who arrived at negative 2 over root 5 for an incorrect reason. This is number 2 on homework 2. The limit in number 2 is a limit as x goes to negative infinity. It is a subtle limit, and the negative shows up, well, with the way I described how to do limits as x goes to negative infinity, it just shows up there. With another way of doing it, it's very tricky where it comes from. So sometime over this weekend, maybe tomorrow, I'm going to send out a page with some information on where this negative came from in number 2. So in the solutions is the way I went over in lecture. I will send something out over the weekend with another way of doing it. And I'll show in there where that negative comes from. It is pretty subtle, which is why I usually don't even like talking about it, but I will mention that. The answer is negative, though.
So this
Number-
and this is problem 2.
2 in homework 2, yes. Number 3 in homework 2. Asked limit as x approaches 0, log 1 minus x. Well, log is a continuous function on its domain, at least. So here, if you want this limit, you could just put the limit inside the logarithm because it's continuous. Let x go to 0, you get log 1 minus 0. You get log 1, which is 0 because e to the 0 is 1. So that's one way you could do it. You could do that on number, 3. You can do it algebraically. You could also have used the graph if you want. Now the graph of this function, y equals log 1 minus x looks like that, goes through 0, 0. So limit as x approaches 0 would also be 0. You could use the graph. Why do I have 2 lines there? Oh, that's the marking point. So you could have also used a graph if you wanted for number 3. I think the algebraic way is easier because you don't even have to think about a graph. Number 4, the details are in the solutions. The answers, I don't remember off the top of my head. I think one was 37/27. But I don't have general comments on 4. The issues with that were more specific, so that'll be part of your feedback. One other thing I forgot to mention in problem 1. In problem 1, it asked for vertical asymptotes, horizontal asymptotes. Remember, these right here are not the correct answers for the vertical asymptotes and the horizontal asymptotes. Because remember, a horizontal asymptote is a horizontal line. And the horizontal line is described by y equals some number. So here, the horizontal asymptote would have been y equals -3/8. And similarly, a vertical asymptote is given by x equals, whatever number. So in this one, the vertical asymptote would have been x equals 3/2. Now, I didn't make too big of a deal out of this when covering it here and when covering in the lecture. So I didn't deduct any points if you just said 3/2 -3/8. But now I am making a big deal out of it. So keep that in mind for on a test if there's a vertical horizontal asymptote question or on the final.
So whenever there's a vertical asymptote or any asymptote, you want us to explicitly say y equals this and that.
Yes. Yes. Yeah. So the asymptote is the line. So an equation. So finding a vertical asymptote, finding a horizontal asymptote is another way of saying find a line. Vertical ones, horizontal ones. So you'll get feedback tomorrow morning. I'm pretty sure, not tonight. Feedback on the homework tomorrow morning. But now I'll talk about the test a little. So the test will be Tuesday. Well, it is Tuesday. I'm going to post it on Canvas at 11 in the morning. I'm going to take it off of Canvas at 5 in the afternoon. It is a 60-minute test. So, you could take it during our, this 2 o'clock to 3:15 period. You could take an hour of that and work on it. But if, another 60-hour or 60-minute block during that 11 to 5 o'clock interval, if another 60-minute block works more conveniently for you, you're welcome to take it then. It will look a lot like our worksheets and homework. There will be point values on each question. There's a page of directions also. But it will be posted on Canvas, probably at the top of the Canvas page in a separate module that says exam or something. But it is going to be available between 11 and 5. So, keep that in mind. Take 1 hour during that, work on the test, and then send me the pictures. Now, what could be on it? Well, anything we've done could be on it. It's a 50-point test. I haven't written it yet. There will be a question on limits, probably between 10 and 20 points on limit computations. There will be one, like number 2 on this worksheet, find derivative using the derivative rules. There will be a definition of the derivative, of course, that's very important. A tangent line is probably going to show up somewhere. The area approximation, maybe it could be find an actual approximation or set up an approximation, or both. The exact area will not be on exam 1. What else did we cover? Graph transformations, they could show up somewhere. Continuity, yes, continuity. So with continuity, we one of the things we did was, given a piecewise function, we forced continuity at their breaking point. Find an a value that makes the one function intersect with the other function at their breaking point. So something like that could show up. General continuity, you can draw the curve without lifting your writing implement, something like that may show up. Trig could show up in some of the calculus things we've done. Trig showed up in limits. It hasn't shown up in derivatives yet. That's going to be after exam 1. But with all the limit things we do, we could ask some trig questions. So I think that covers everything. There's, in preparing for the exam, worksheets, homework questions, when an exam is written, I
For the
based on all the
professor.
code, and then do some things.
Professor,
Yes.
for this continuity, the kind of what are kind of questions are going to be asked like?
Well, we've covered, so in the continuity lecture, what did we do? We covered, well, first of all, this down here is, this equal sign is from continuity, that you can do a substitution. But the other context of continuity did were find a value a that makes a piecewise function continuous. I believe that was not on the homework. That was on worksheet 3 though. So something like that could show up. And the interpretation of a continuous function being, one that you can draw essentially in one piece. Something like that could show up. Forcing continuity at a point by making the limits equal the function at the point. It would be an application related to, one of those, or maybe something directly like one of those. I haven't decided yet. It could also be, we talked about discontinuities. It could also be the discontinuities. Toward the beginning of the continuity lecture, we described discontinuities. There could be a question on those. So that would be, this would be a discontinuity where the limit exists but doesn't equal the function. I think that covers everything we did in continuity. Any other questions? Okay, well, this weather is what is commonly considered good weather, even though I don't like it. So I do hope you enjoy your Thursday, and definitely enjoy your weekend, but spend some of it at least thinking about calculus and preparing for your test on Tuesday. 50-point test. How many points for this? That's 300 points. So this is a 1/6 of your grade on Tuesday. So enjoy your weekend. And let me know if you have any questions. So thank you for showing up for this.